Hello and welcome once again. In the previous two modules, we had some detailed discussion regarding functional programming in R. We had discussed explicitly what anonymous function is, what closure of a function is, and many other things. We had taken up some examples to let you know the detailed description of these functions and so on. In this current module, we are going to discuss something about what list of function actually is, what is mutable state is, and many other things. So, let us start the discussion and let us find what is there in this module. So, let us start with function factories. Now, as we know, one of the primary work of Clojure is to make function factories. Now, with the name, you must have got some ideas about what this actually is. So, let us consider it a bit explicitly. At first, start with the cases where this might be used. This can be used primarily when the different levels are more complex, that is, it contains multiple arguments and also complicated bodies. One other thing is that some work are required to be done only once, and that too only when the function is generated. In these cases, function factories are most useful, as we all know that the function factories are specifically used to get maximum likelihood estimates. We will discuss this matter a bit explicitly during the end of our module. We will take up some examples in order to elaborate this. Now, you may often find its application over some different spheres of statistics. So, during our entire discussion on functional programming, we had used some examples of function factories. Before this, when we were discussing about ways of fixing missing values, we came across these kinds of functions. Again, the root function that we had used is another instance of function factory. In that case, what we did is we called the function with arguments, and those arguments actually shows the actions that are needed. Moreover, these functions return a function which actually helps us to do the necessary work of this function. In those examples, you might have observed that this function is not going to give you much other than a single function with multiple arguments. In the case of root function, as well we had seen just the same, where a single root function is used with different exponents half and 1/3, which provided us the square root and the cube roots of different numbers respectively. We will show you some more examples of function factories later in this discussion. So, let us take up this. So, let us start with some more examples of function factories, as we just said. Remember, with the help of closures, we can create functions that will lead us to do all complex works which are similar for all functions, and also to define the functionalities of each of the functions by writing specific functions. Now, let us concentrate on the example. Suppose our objective is to add values x to the value I, which keeps on changing. So, we need to find x plus y. This is really a very elementary problem, as we all know, and which can be solved using a number of ways. So, let us take them up one by one. One of the ways of handling it is we can define a function sum, which is a function of x and I, and we are just adding x with I. Now, keep on changing the values of x and y, and you will get the output that we have shown here. We can make it a function of I initially and then the function of x gradually. So, our function will look like this. Here at first we are declaring it to be a function of I, as we have just said, and then our function of x, and finally we are adding up I and x. We keep on changing the values of I and x. So, here we do not need to write down all the g1, g2 functions separately. The gi's will cater the job. Here only we need to do something. So, what is this? Let us write g1 as g of 1 and following the similar fashion define g2, g3 and so on. Now, if we write down g1 of 5, then we will be having 6, and so here actually 5 is added up with 1 and we are getting 6. Similarly, g2 of 7 will result 9 as 2 it added up with 7. Here an interesting thing is whenever we are assigning g of 1 to g1, it may look like a variable, as we all know, where some value is assigned, but actually this is not a particular value. Instead, this is a function which will provide particular value whenever we put some value within it. So, we are not at all getting a variable, we are getting a function. So, after going through this example, you might be thinking, why am I considering this? Is not it increases the complexity of the problem? Yes, exactly. Indeed, this problem might be solved with much simpler ways, but we need to go through this problem so that this experience might help us to handle more complex problem more elegant. Now, we are taking up another complex example and let us find what is happening here. Here the objective is to compute maximum likelihood estimates for some well-known distributions when a vector of data is provided to us. Within the function estimate underscore new, we defined another function which is initial underscore estimate. Now, this is a function of x and theta, but estimate underscore new is a function of the distribution for which we are intended to find the maximum likelihood estimates. So, these are very clear to us. So, the initial underscore estimate function will depend on the distribution that we are choosing. Within initial underscore estimate, we are defining another function that is neg-like, which we will minimize later with the help of optim function. So, optim function is basically dedicated to optimize a function. The function initial underscore estimate can be used as a generator of maximum likelihood estimation functions for any distribution as long as its corresponding ddist function exists in R. So, it has to be there in R. So, whenever we have the function estimate underscore new, we can use it to define any maximum likelihood estimation function whenever its density function is defined. So, this is the condition. So, let us consider the distribution which we often come across during lifetime studies. Here, the function L-Weibull computes Weibull maximum likelihood estimates. Here we have generated a sample of 100 data points from Weibull distribution with parameters 2 and 1. These are very simple, and here is the code, and we are storing these data points within W. Here, just by putting d-Weibull as the argument of the estimate underscore new function and using the code as it had been shown here, we will come up with the parameter estimates of the Weibull distribution. The example can be constructed for some other well-known distributions as well, like we can take up gamma, log normal and many more distributions. Now let's take up something which is even more interesting. So let's see what happens next. Here we are considering the moving statistics. The idea is to return a moving function considering simple functions like mean, median and many more. Have a close look at the example which we will be going to discuss now. Here we are considering the function func, which is a function of I, x, and a function f, which will be decided later. So these are the arguments of the function func. The body of the function says that we need to apply the function that was there in the argument to the values of x starting from the I minus 2th value, and we are going up to the ith value. So this is what the function is saying. Now let's see what happens when we start putting the arguments within the func function. Here we are taking I is equal to 4 and x contains the values from 1 to up to 8. So these are the arguments. Here the function that will be used is min. So what func doing is that it is taking the values starting from the second and going up to the 4th value of x. So we are considering 2, 3 and 4, and then we are trying to get the mean of these 3, which is 3 itself. We all know that the mean of 2, 3, 4 will be 3. So it's very simple. So this is the answer that we are getting here. Now we are considering the next sets of arguments. Here other arguments remain same. The only difference lies in the function that we are using. Here we are using the function standard deviation in order to deal with the data, and the output will be 1. We can also define a function called moving that might take any function as input and define a function func within its body. The function which is shown here has actually been made using this idea. We will handle many more things starting from this, but let's stop this discussion of moving function here, and we will continue it again in the module where functionals will be discussed. In the next few modules we will start discussing the ideas of functionals. So let's stop here. Now here comes the idea of mutable state. Consider the function count underscore call. The idea of this function is to count the number of times a function has been called. Observe it minutely to understand how is it working. Whenever we run the function count underscore call, an environment has been called. It starts with the initial count 0, and then as we can see here, a new function has been created. Actually, as we know, we need to deal with two different environments here, and whenever we are refreshing the execution environment, the enclosing environment remains fixed. Now the question is, how will we do this? We can do this primarily with the double arrow assignment. It seems a bit alien to most of you because in most of the cases we use the single arrow assignment, isn't it? But the two are meant for two different things, as we can understand. The single arrow assignment always assigns in the current environment, but the double arrow assignment, that is the one used here, handles primarily the parent environment. It always keeps an eye at the chain of parent environment until it finds a matching name. In the example which we just mentioned to create counts, the new function is a closure. Then what is it actually enclosing? What is the enclosing environment here? The enclosing environment is primarily the environment that is created when the count underscore call function is run. Now, as we discussed earlier, the environments are destroyed after the execution for an ordinary function, but a closure always contacts with the environment where it had been created. That is the environment which is called its parent environment. In this example, count1 and count2 maintains two separate counts. Whenever we are running the function, each of count1 and count2 will get the environment in which they are enclosed. This is the reason why we are having different counts after calling this. But the function that we just discussed do have some limitations, one of which is it does not have a fresh start. If you think of the reason, you might find it easily after having a closer look at the function body. Here, we are not modifying the variables in their local environment. Actually, the changes are made in the enclosing environment which are not changing. So, these are retained all along the function. Here, count underscore 1 is a function where we are not actually using a closure, and count underscore call 2 is a function where we are using a single assignment operator, unlike the double which we discussed earlier. We may also put the function in a different way which will be even more easier to understand. So, let us consider this. Following exactly the same logic as it had been there in the previous example, we are starting with a function count. We are starting with count 0, and then the function is being written in such a way that each time the function is called, it will come up with its position of coming along with the time at which it is being called. So, this is how the function looks like. So, whenever we call the func function, it will show you the time at which it is coming as well as the number of times it has come, including this turn. So, from this discussion, we do have some ideas about mutable states. As we just have discussed, the modification of the values in the parent environment primarily helps you to generate mutable states in R. Whenever you are using a mutable state, it seems that you are changing an object every time. The reality is that you are primarily modifying a copy after its creation. So, this is the logic behind its work. However, we will introduce you to some other ways of handling mutable objects through the use of reference classes. So, let us have a look. Let us start getting the ideas of one of the most important components of functional programming, which is called list of functions. The idea of list of functions in R, like any other kind of R object, can be stored in a list. This is the idea. So, how does it help? It actually helps us to work with a group of related functions. List of functions helps the user to deal with the sets of functions that are close-knit in some sense. So, do you find any similarity with something else? Actually, this is pretty much similar to the data frame. The only difference is, in case of a data frame, we generally use a group of related vector, and here, unlike the vector, we are dealing with some related functions. So, let us consider this function with the name list underscore function. It contains two summary functions. One is mean and the other one is standard deviation within the list. Now, the function which are defined within a list, that is the summary functions like mean and standard deviation in this case, are still accessible at least in three different ways. So, let us consider them one by one. Firstly, let us consider the with function. Suppose we want to access the mean function from the list underscore function. Then what do we do? What are the arguments that we need to put inside the with function? we need to put the name of the list, then the function we want to have access, and then the numbers or the data to which the function will be applied. This whole thing within the with function will be there. So, we are trying to find the mean of the first 10 integers starting from 1 through this function, and here is the output. Another way of assessing it is through the well known dollar operator. We all know that. In this case, what we usually do is we write down the list name, then extract the function from it through the dollar operator, and then within the argument put the numbers we want to deal. It is needless to say that this method is something which we can easily relate to, because we all of us are familiar with this method. One final way of looking at this is by attaching the list, then accessing the function. The code which is shown here are exactly giving the same thing. Here it is always advisable to detach the list from the environment after using. Another important way of using the list function is by applying all the functions of the list to the same set of data. We can execute this by some easier ways. So, let us see how it works. Use 2 steps to do this. So, at first, this is the first stage. The syntax of the function will be like the one we had given here. Here what the function does is it takes function f as argument along with any other arguments which are given through dots and returns the function f. Here we are writing a function mean within the function fun and also specifying the data on which the mean will be calculated. Now, what we are doing is we are applying the function fun to the list of functions. Here the arguments that the function is using are stored in the list and are passed by the dots of the function arguments. This is how the whole thing is working. Using the Laplace function, we are having access of both the functions enlisted within the list, naming the list underscore function. Here, if we use the do.call function within the Laplace function, then also we will come up with the same result. The only difference is that the arguments to functions within the list must be enclosed in a list too. Like here, the list underscore function follows this. Let's start with another well-known example. Arithmetic mean can be considered as one of the simplest summary statistics that one can think of. We all know that. In the present discussion, suppose we are trying to accumulate the different ways of computing the simple arithmetic mean. Since the function is very simple, so you can expect lesser amount of computational complexity in this regard. Now, what we can do is we can store each of the method that you are applying in a list, and hence we can make a list of function. So, let us see how it works. Let us name the function mean calculation with an underscore between mean and calculation. Here altogether we are taking up 3 different methods of obtaining arithmetic mean. As for method 1, we are declaring mean of x as a function of x. So, straight away we are using the base package to obtain the mean of some numbers. In case of method 2, we are dividing sum of x with the length of x, and as in method 3, we are starting with a total of 0, which is the initial value, and then we keep on updating the total by adding up the x values within a for loop, and then dividing the whole thing by the total number of observations. So, these are 3 ways that are shown here to calculate the mean of x. Here, as we are going along from method 1 to method 3, the functions are getting more and more elementary. Remember, in the first case we used the base to compute mean. Anyway, let us concentrate on the function. Here we are putting the three methods that had been constructed to find mean within the least function, and hence we obtained the mean calculation function, which is actually a list of functions. So now the function consisting of three methods to find mean have been constructed. So our next issue will be to use it properly, and for this we need to call it at first. At first, suppose we are generating 10 numbers from standard normal distribution, and this is our x. In the previous example as well, we had shown different ways to extract functions from a list of function. So here let us apply that. If we want to extract, say, method I from these list of functions for all I is equal to 1, 2, 3, then what do? We will either type the first one, that is by using a dollar sign, or by putting the function number using the third bracket twice, or we might put the function name treating it as character. So this is how the output will look like. Now in this regard, here I want to mention that we can always calculate the time taken by each of the functions to calculate mean, and then can comment on the efficiency of the three functions. Now as it had been done earlier, here as well we can use the Laplace function. For this you just need to write down this code where the list of functions mean calculation has been used as an argument. And finally, we are coming up with the means that are calculated using all the three methods. And obviously, it is needless to say that all three of them are equal. Here comes one other use of using a list of functions. Primarily, it is some finer tuning of summarization. By now, we are habituated with this. So, we had seen these in one of our previous examples as well. But this example offers us some more with respect to the previous one. Here we are starting with 10 points that had been generated from uniform distribution, and following our previous notion, we are constructing the least of function and we are naming it as least functions with an underscore between least and function. We are only including the functions mean and median over here. We are not getting into complicated things, so we want to make it simpler. Next, by using the Laplace function, we can always obtain the two summary values separately. Here comes the additional aspect which we are intending to mention. Suppose you are dealing with the values that include missing observations. So these values are going to disrupt our summary values, as we all know. So what do? Here we may seek the help of anonymous functions which will be true inside the list, and the arguments would include na.rm is equal to true. We know that we had used it previously as well. And then by using the Laplace function, we would come up with the summary values even if we are given such a set of values which contains missing observations. So these are the additional advantages. Now let us take up another example. Here the idea is to develop a simple numerical integration function using first class function. We are trying to reduce duplications as much as we can. As we know, this is what the idea of functional programming is. One of the ideas of functional programming is. Now we all know what the numerical integration means. The idea behind numerical integration is to find the area under a curve by approximating the curve with similar components. We know that. We all know what the simplest approach is. Actually, it is the trapezoidal rule. We have studied many things about this thing. Here, the area under the curve usually gets approximated with the trapezoid. So, if we want to integrate the function sin x, say, where the range of integration is 0 to pi, then we need to put these information in place of the arguments of the trapezoid function, and then we can calculate the value of the integral in a moment. These are pretty simple now. But we are not reaching at a point where this function is giving us a very good approximation. So, what do? We are concentrating on the process of making it more and more accurate, and hence will use some composite modification. The functions that we have given here provides us some of the modifications, and they are actually showing how we can break up the range of the integral into smaller pieces and integrate each piece using one of the simple rules. And this is how we are modifying our previous function. In this module, we had some more detailed discussions about elements of functional programming. Here, we came to know what mutable function actually is. With some examples, we have some detailed understanding about list of functions and many more. During the last part of the discussion, we have taken up the example of numerical integration in R with trapezoidal rule. So, we have some great understanding of this now. We are wrapping up this discussion of functional programming in R, which we had started, which we had continued since the last 3 modules. We are wrapping up this discussion now, and from the next module onwards, we will start the discussion of functioners in R.